Right now, NVIDIA is reportedly weighing a massive financial backstop for a single OpenAI facility. We're talking up to $250 billion in financing to guarantee the lease for one endless, centralized AI hub. To understand why a single project could require $250 billion, look at the physical blueprint. The proposed facility demands 10 gigawatts of power. That's enough electricity to run several major cities, all funneled into a single cluster of servers. Securing the world's fastest silicon chips is no longer the main hurdle. The actual constraint in the AI arms race is finding electricity to turn those chips on. A single future AI accelerator rack will draw up to 240 kilowatts. This chart shows projected global electricity demand for AI data centers. While traditional grids expand slowly, AI's energy appetite scales vertically. By 2030, global demand is projected to hit 945 terawatt-hours annually, matching the entire electricity consumption of Japan. Software developers have suddenly run headfirst into a physics problem. These massive training models are simply outgrowing the physical limits of our existing public electrical grids. Tech giants can't just build coal or gas plants to fix this. They have all made strict public net zero carbon pledges, which completely removes heavy-emitting fossil fuels from their long-term growth equations. At the same time, AI training runs require 24/7 continuous power. If an AI cluster is pulling 500 megawatts, it cannot tolerate a voltage drop when the wind stops blowing or a storm rolls in over a solar farm. Intermittency ruins the training process. Relying on the public utility grid isn't a solution either. Waiting for major transmission upgrades takes years. And when developers try to build massive facilities near residential grids, local communities actively resist them to avoid water shortages and spikes in electricity prices. The math leaves these companies with exactly one option to prevent AI development from stalling. They have to circumvent public utilities entirely and become sovereign, independent power producers. To secure that grid-independent, carbon-free baseload power, the tech industry is committing over $10 billion to trigger a commercial nuclear renaissance. Microsoft is taking an extreme immediate approach. They recently signed a 20-year agreement to literally restart Unit 1 at 3 Mile Island, securing 837 megawatts of dedicated power by 2028. Restarting dormant plants covers their short-term needs, but there are only so many old reactors available. The long-term strategy for the entire sector relies on commercializing a totally different approach, small modular reactors, or SMRs. The financial bets being placed on this next-generation tech are staggering. Amazon is pushing for 5 gigawatts of SMR capacity through a $500 million investment in X-Energy, while Google has established a milestone 500-megawatt order book with Kairos Power. By putting billions of dollars on the table today, tech giants are providing the exact market signal manufacturers need. That guaranteed capital is what takes experimental nuclear physics out of the laboratory and pushes it into commercial assembly line manufacturing. Traditional nuclear plants are custom-built on site over the course of a decade. SMRs take that exact same carbon-free power generation, shrink it down, and shift the construction into a controlled, standardized factory environment. Instead of pouring concrete for 10 years, these standardized components are shipped directly to the data center site and assembled in just 24 to 36 months. And because they're modular, a facility can scale its power output block by block as its computational needs grow. They also utilize passive safety systems. If an SMR ships down, it uses natural physics like gravity and convection to cool itself for days. It doesn't rely on external power grids or human intervention to keep the core stable. When paired directly with an AI data center, the efficiency goes even further. The reactor provides massive electricity to the GPUs, and the extreme waste heat generated by those servers can be captured and repurposed for local district heating, pushing overall system efficiency past 80%. By standardizing the design, SMRs turn nuclear power from a risky, bespoke megaproject into a predictable, mass-manufactured product tailored specifically for the AI boom. This deployment won't happen overnight. First-of-a-kind SMR projects still face brutal capital costs, running up to $6,000 per kilowatt. On top of that, advanced designs require high-assay, low-enriched uranium, a specialized fuel currently facing severe supply chain bottlenecks. But the red tape is already being cleared to win the AI race. In the US, the ADVANCE Act has slashed regulatory fees and mandated rapid 18-month review timelines for new reactor applications, cutting years off the historical process. The physical timeline is already moving. TerraPower has broken ground in Wyoming on the first commercial advanced reactor in the U.S., targeting completion by 2030. This convergence creates a new requirement for technological leadership. The ultimate advantage in the AI era now belongs to whichever organization can first master the physics of securing and delivering gigawatts of carbon-free power.